All right, we'll go ahead and jump in, and hopefully some more folks will join us. But regardless, we're going to have a good session. We're going into some scan tool power features tonight, ways to make your scan tool usage more powerful and efficient. And we're going to go into some diagnostics and get you guys introduced to fuel trim. And so we got plenty of stuff to cover. I just wanted to start here with this home screen. Always when you're here, make sure you take a quick scan of what the announcements are, what's going on. Remember, we're going to have a class session about every other week, and we're just about we're halfway through the semester now. We are on our fourth class Zoom session, and we're going to have a couple more, and then we'll kind of wrap this up and open up the Snap-on training. So let me clear those drawings and let me go to modules and just kind of show you guys where we're at right now. So obviously we've gone through that. We've pretty much wrapped up our beginning weeks and scan tool information, and we're now well into the core of scan tool data and diagnostics. So we're moving through this this section right here. Now, some of this stuff we've already talked about a little bit. So you guys probably already know some of the stuff like the 8-step scan tool diagnostic process. We're going to go over that again tonight. You guys have been working away on your various quizzes here on Canvas, and you've been getting some great scores, which is fantastic. So we're kind of transitioning between the core more to the advanced stuff as we go into tonight's presentation. Welcome to Zoom tonight. So just kind of reviewing the modules here. And so, like I was saying, we're transitioning from what I'll call the basics and the core of like using a scan tool, codes, data, basic troubleshooting process. And now we're moving it more into the advanced stuff. So with that, let's open up tonight's presentation. So I'm going to change my screen share here. And tonight's presentation is maximize your scan tool. Whatever scan tool you have, even if you're just limited to a little cell phone app using our interface, we still want to get as much diagnostic power as we can out of this thing, right? So whatever tool you have, I always recommend read the manual, look for online training, try to become a power user of that tool. And so this is a great screen right here because we're actually graphing out some data, and we'll talk more about that as we jump into this thing. So I'm going to change things up a little bit and make my screen share a little bit cleaner. And let's dive in. All right. So the 8-step scan tool diagnostic process. We've talked about this one before, guys. Don't forget that, over time, you guys are going to develop your own diagnostic process, which is good, which is what I want you to do. But, when you're getting started, diagnosing cars can be somewhat overwhelming. And so I put this together as a basic process to get you guys started down your diagnostic pathway. So whatever you're trying to diagnose on a car, the first thing's always verify the complaint, right? Imagine if a customer came in and they said, hey, my car has a vibration, right? You would go for a test drive and see if you could feel the vibration, thereby verifying the complaint. Yeah, there is a vibration. For us in this class, we're doing scanner diagnostics. So normally the person's going to complain that the check engine light, or the mill as we call it, the mill is on. So we verify that that light is on. Sometimes they might be complaining because they have a drivability problem. This would be something like a lack of power, or it runs rough, or if they're really conscious, maybe they notice that their fuel economy is going down. So we verify, yes, the car has the problem, the check engine light is on, whatever. And now with our scan tool, we're going to pull codes. And I always say record because that means write this information down. The nice thing about a cell phone based app is you can always do a screenshot on your phone. And so it's a quick way to record what's on there. Back in the day, I used to use paper and pencil and write stuff down. And then I actually spent extra money to have like a serial cable for my scanner. And it was super clunky to connect my scanner to the computer. But anyways, you always want to record that information. And now, remember 4 and 5, we might switch the order of these. It depends on how familiar are you with that particular car, that particular problem. How well do you know your scan data? So if you're pretty comfortable reading scan data, then I'm going to jump right into scan data and see, does the scan data support the code? If I'm not sure and I got to do some research, well, then I'm going to jump into my service information to try to figure out what the scan data should look like. Let me give you guys your first tech tip of the night, and that's going to be this right here. So, tech tip. Look at normal data. Okay, so let me explain this. The tech tip is to look at normal data. Why? Because we need to know what normal looks like. If somebody brings their car in and they say, oh, their complaint is maybe not that the mill is on, but they have a drivability complaint, right? Maybe they say that they have a lack of power. Okay, there's my shorthand there for power. Say a lack of power, you start looking through the scan data. If you don't know what it's supposed to look like on that car, well, you're going to be stuck. You need to know what normal good data is going to look like, what it's supposed to look like, I should say. What should those data PIDs look like? So here's what I recommend you do, is every car that you get a chance to look at, you put your scanner on there. Even if it's just this little generic interface, put your scanner on there, scan it, take some screenshots of the data. So I would have, cars come in I hadn't worked on before. It's just in there for an oil change, maybe a tire rotation. I would take an extra 5 minutes and check it out with my scanner. And I would pull some screenshots of the data. I would start looking at it, recording it if I had a tool that was capable of doing that. At the very least, you could scan it, take pictures of the screen with your phone. But I would start recording, what does normal data look like on this car? Then I took those recordings and I saved them on my computer with the different makes and models. Okay, so this was a 2002 Nissan Maxima. That's what its data looked like. So I would purposely scan cars that had no problems with them so I could establish what the data should look like. So when a car came in that was like that had a problem, I could see how it compared to normal. Okay, so your tech tip is look at normal data. Look at cars without problems to establish what normal is. That way, when you're afflicted with a car that's driving weird, check engine light on, you'll have a baseline. All right. So you go back and forth between looking at your service information and looking at your scan data. Ultimately, you're going to go through a flow chart or something, and you're going to do some pinpoint testing. This is where we're using our multimeter. We might be using an oscilloscope to isolate what exactly the problem is. right? Pinpoint testing. Ultimately, then we need to get our customers' approval once we make our diagnostics so that we can perform repairs. And remember, because we always care about the quality of what we're doing, and we want those customers to come back to us, we always verify those repairs when we're done. And that means that I'm going to have to test drive the vehicle, and I'm more than likely going to have to drive it not just around the block, but drive it in such a way where I meet, remember what we call it? I meet the enable criteria. Or I should probably put, I meet the conditions, necessary conditions to get the monitor to run. And then we'll have a trip performed. Then we can go in there, we could pull mode 6 data, we could look for pending codes, and we'll know without a doubt whether or not we've truly fixed the problem. We can even identify some other problems, because sometimes what will happen is you'll have one thing affecting something else, you fix that, then the computer does some more tests and figures out some other stuff that it doesn't like. So this is our 8-step diagnostic process. We're going to keep applying this over and over. And then, you know, as time goes on, what you guys will do is take this process and modify it to make it suit your style or the cars that you're working on, that type of thing. But it gets you going, hopefully, the right direction. And that's one of our upcoming homework assignments. It basically asks you, hey, what's the diagnostic process? Boom, here it is right here. You could screenshot this thing right now. You could cut and paste, copy this down. That's the answer to your upcoming homework assignment right there. Okay, moving right along. Remember, we talked about how our multimeter is front door information. We're testing the sensors and stuff directly. Scan data is backdoor information. It's processed by the computer. So we always have to keep that in mind to make sure that the scanner is not lying to us. We talked about how an OBD2, it's not supposed to lie to us. And it usually does a better job than that, than the manufacturer side of the tool. But we still always have to have a little bit of caution, because it is processed data. It's data that has been processed by the vehicle's computer system. All right. So that was all really review stuff. Last bit of review, we like to say that our scanner is like our directional tool. It's a compass. It gets us going the right direction. More often than not, we're going to need a multimeter or an oscilloscope to pinpoint that exact cause of the problem. Okay, so front door input sensors or front door information. All right. So I've already kind of went over this a little bit, right? But check engine lights on. Of course, we're going to do the first 3 things. And I'll tell you what I see people see, what people skip over way too much is they see, oh, this check engine light's on. And they see that. So they verify, okay, they've done that. They pull the codes. And you know what they see people do all the time? They don't write the codes down. They don't look at the freeze frame. They just go and they clear the codes. And they're like, oh, I'm going to clear the codes and see what happens. And it's amazing how many people I see do this still to this day. Now, back in the 80s, and I'm dating myself here, but back in the 80s, back in the days of OBD1, and I know a few of you guys do have OBD1 vehicles. So this was the process. You would pull codes, then you would clear the codes, and you would see what came back. So I'm going to say hard versus soft. What am I talking about here? Well, back in the OBD1 days, you would have a car, you'd pull the codes, you might get a whole bunch of codes, you would clear them, you'd write them, you'd always write them down. I'd always write them down, I'd clear them, and I see what came back. The codes that came back were considered to be hard codes. And so I dealt with those first. The codes that came back, that didn't come back, the codes that did not come back, those were soft codes. And those could have been set by somebody's brother-in-law unplugging stuff because they're like, oh, what's this do? You know, those were codes you didn't worry about. That maybe there was a problem, likely there wasn't a problem, and you focused on the hard codes. That was the strategy on those cars. Remember, they didn't have monitors. The computer was checking for what they call normality. It was basically looking for circuits that were opened and shorted. Anyways, a lot of people will take this old strategy and apply it to OBD2. And the reason we don't want to do this, so now I'm going to put a circle, cross it out. The reason we don't want to do that on an OBD2 vehicle is when we clear the codes, we lose our freeze frame information. Oftentimes, we'll not only lose the freeze frame data, we'll lose all the monitors. So those all get reset, and we lose a ton of diagnostic information. I don't clear the codes until after I've done my repair and I'm feeling pretty good about that repair. I clear the codes and then I go for my test drive. So right here, that is where I clear the codes. Why? So that I can make sure I know what that freeze frame data is so I can know how to drive the car again to really verify my repairs. Anyways, a lot of people will clear the codes, and then of course the car doesn't set an OBD2 vehicle. It's not going to set a code right away oftentimes because it's probably a type B code. Most codes are, and they go, oh, well, maybe there's nothing wrong with it. And then the person takes it and they drive it a few days, and a week later the light comes on, and then they're back at the shop or back at their friend's house scanning it again. Well, it's not like the problem was ever gone. It just took them that much driving around to meet the enable criteria to get the monitor to run. And remember, for a type B code, it takes 2 consecutive failures to turn on the check engine light. So again, follow our procedure. Don't clear the codes. Pull the codes, write them down. Record the freeze frame data. Then start looking at your scan data and going on with your diagnostic. All right. Do not clear the codes. Boom. All right. So sometimes you're scanning a car and it can be overwhelming when we get to step 4 here and we're looking at the scan data, because maybe you're working on a newer car and there's just all kinds of data. Even with your generic scan tool, there might be all kinds of data that's overwhelming to look at. So we're analyzing the data. How do we best do that? Well, this is where we get into what I call the big 6, or a lot of times the big 6 has grown and now it's more like the gray 8. You'll see what I mean here. So what you can do is you can set up on almost all scan tools, you can set up what we call a custom data list. In that, I only want to look at the things that I want to look at. So you can see here we're on a Solus Ultra, Snap-on Solus Ultra, and there's all these different things. What I can do here on this screen on this particular tool is I'm checking the ones that I want to look at. So I could say, okay, I want to look at engine RPM, and I want to look at the mass airflow. And so when you're building a custom data list, what I like to do is pick 6 or 8 items to help me establish a condition. What does that mean? Well, I want to establish a condition if I have a drivability issue, like, is it running rich, right? Getting too much fuel is what that means. Is it running too lean? It's not getting enough fuel. Okay, so is it running rich? Is it running lean? Does it have a misfire issue? So I want a direction. Establishing condition kind of gives me a direction on where to go. And so to help me establish that condition, these are the normal parameters I'll look at because they tell me a lot about how the engine is running. And the nice thing about these 6 parameters is that you can access all 6 of those with a generic scan tool on an OBD2 vehicle. So there's my basic parameters. Now, sometimes, especially if I'm having a problem like starting, the intake air temperature sensor is a big one on that initial start calculation. So I might throw him on there. And I also kind of compare the intake air temperature to the coolant, especially when I'm doing a cold start. And I also like to look at load, so I know how much load I'm putting on the engine. So here I got engine load right here. This engine's at 21% load. Now that's a calculated value. How does the computer come up with that? Well, it looks at throttle position, it looks at mass airflow and engine RPM, and it works all those together to figure out how much load or how much strain, how hard is the engine having to work. Okay. Now, why this list will then grow. So we have 6 here. We've added these on. Now we're up to 8. Sometimes it might even grow even more because the O2 sensors and the fuel trim can get bigger. If I have, and I'll change the color here to just mix it up a little bit. So if I have a V type engine, it could be a V8, a V6, I'm going to have a bank one side of the engine and a bank 2. So now it's not just one O2 sensor, I'm looking at 2 O2 sensors. Now, maybe I got O2 sensors after my catalytic converter, and I want to look at those too. So maybe I have up to 4 oxygen sensors. And if I have fuel trim, if I have 2 banks, I'm likely to have a bank 1 fuel trim and a bank 2 fuel trim. So the O2 sensors and the fuel trim can kind of grow on you, and you end up with maybe 10 parameters or so. But these ones are pretty good to get you a good indication of what's going on with the engine and how is it running. Okay, let's clear those scribbles out. So the big 6 and the great 8, those are good parameters. Engine RPM, mass airflow, or MAP. If it does not have a mass airflow sensor, it only has a manifold absolute pressure sensor, then I would look at that. Again, that's letting me know about the load. Obviously, throttle position, coolant temperature, oxygen sensors, fuel trim. Now, some of these things you might be thinking, well, I'm not sure what these things are. Well, we're going to talk about a couple of them tonight, namely the O2 sensors and the fuel trim. Those are pretty important. Real quickly though, mass airflow, it's telling the computer how many grams per second of air is going into the engine and what the density of that air is. And MAP sensor, it's kind of like the inverse of an old school vacuum gauge. The higher the manifold pressure, the lower the vacuum, meaning that the more air is going into that engine, and that means it's under more load or strain. And what you'll see is that your mass airflow or your MAP sensor, they move in unison with your throttle position. So if I step on my gas pedal and I see my throttle position moving up, right, as I'm opening up the throttle, I should see my mass airflow go up as well, or my manifold absolute pressure, I should see that go up. So those guys, and really, if you think about it, we could plug all 3 of these together. As we open up the throttle, we should see the throttle open up, the engine RPM increase, and so should the mass airflow. All those things should move together. So a quick check is to do just that. Work the throttle and see, do those 3 items work together? Are they moving up and down in unison? Because they should be. All right. So moving right along. Here you can see on this particular tool, this is the Snap-on Solus Ultra. I'm clicking the ones that I want to build that custom data list. Now you might be thinking, well, why would I need to do that other than, okay, I got so much data, it's kind of overwhelming. Well, this brings us back something that we talked about earlier. And I'm just checking the chat real quick. So the question is so is base data similar to live data after having performed? So the freeze frame data is the data that was stored when the code was set. And what you want to look for is after you're done with your repairs, drive it around similar to how it was being driven in the freeze frame. So if the car was, let's say, under 30% load at 60 miles an hour with a hot engine in your freeze frame when the code was set, I would drive the car the exact same way to try to recreate that condition. So hopefully that answered that question in the chat. All right, so back to this thing on the custom data lists. And actually, let me go back a slide. The custom data list is even more important on an older vehicle. Why? Because of the communication protocols and what that protocol's baud rate is. Now, baud rate is how quickly are the ones and zeros, how quickly are these data bits traveling between the computers on the vehicle, and how quickly are they traveling between the computer in the vehicle and your scan tool. So you can see, like if you have an older GM, like my 96 Chevy, it's down to 10.4 kilobits per second baud rate. Pretty dog slow, to be honest with you. Now, J1850 on the Fords, that was on the faster end. It was up to 41.6. You can see the early ISO, again, 10.4. Toyota, a lot of companies use that. Most cars that you guys are going to scan now, right? Most of your new cars are going to say 2008 and newer are likely going to be CAN, Controller Area Network. And I had that activity where I said, hey, what is your protocol? And we looked at that before. Well, this is a big deal. If I have a newer car, it's got really fast data transmission back and forth between the scanner and the car. And it works pretty sweet. But on older cars, if I have an older car and I'm limited here, I'm limited to 10.4 kilobits per second, that's pretty chunky. And so by setting up a custom data list and not asking the computer to send all the data parameters, only asking it to send a few data parameters, those big 6 that I was talking about, it will speed up the data refresh rate of your scan tool considerably, and make it work much more smoothly. You're less likely to have a glitch happen and totally miss it, meaning that you're more likely to catch a glitch if a glitch does happen. So especially on the older cars, custom data lists were even more important because the computers they were slower, they were older, right? And this is a picture of our OBD2 connector right here. And you can see that different protocols actually speak on different pins of the data link connector, of the DLC. Of course, pins 4 and 5 are always ground, 16's always power, but you can see the other ones, it skips around based upon what's your communication protocol. Okay. So custom data lists. So here we're looking at Snap-on again, and we got a custom data list, but not only are we doing a custom data list, we are graphing that data. And I love to graph the data because it makes it so much easier for our human brains to interpret that, right? If you have like a digital tachometer and it's bouncing up and down, that's really hard to interpret. But if you have an analog tachometer, and that's why cars still to this day, a lot of them still have analog gauges because it's easier to see that and see that movement. Well, if I'm dealing with digits, if I graph it out, it makes it easier for my brain to see the movement, and you're going to be more likely to catch a problem when you have data graphing on. So here we've selected engine speed, the mass airflow. It's also got a map sensor and an oxygen sensor. We're looking at those 4 parameters on a custom data list, and we're graphing those out. So the data list allows you to choose what you're going to look at. Graphing them makes it easier to see. And let's face it, this stuff's complicated enough. Anything you can do to make it easier for you to see the problem is going to be a step in the right direction. Okay. So now we know that, hey, we can customize our data list and just try to look at the items we're interested in. We know that graphing the data is really important to do because it helps us identify problems a little bit better. But this doesn't get us around the fact that we have to have some pinpoint knowledge, circuit knowledge, to really diagnose these problems. But with that knowledge, I can really speed up my diagnostics. So I put together a quick example here for engine coolant temperature sensors. Okay, it starts with good circuit knowledge. So here's a picture of a vehicle. There's the coolant temp. Screw it into the thermostat housing area. Notice it's a 2-wire sensor. Okay, and these have been that way for 30 years now. So not a lot of changes on these guys over the years. So here is the wiring diagram for that. And the question is, how would you test it? Well, I have been telling you that, hey, you got to get your meter to do pinpoint testing. But if you know how the circuit works, maybe you can cheat. And you know what? I like to cheat whenever possible. Why? It's hard enough working on cars. You got to figure out the shortcuts to really be successful. Okay, so I drew this diagram out, and you can see that we do have our meter over here. And so you could hook up your meter and get them hooked up and all that stuff. But realistically, although it's easy to draw a meter being hooked up, to really hook it up, I got to get my meter leads out. I might have to back probe the connectors or use jumper wires. Getting a good connection here could be a pain in the butt. So if I don't have to mess around with my meter, I would like that better. It would save me some time. In fact, it's a lot easier to hook up my scanner and get my scanner going than it is for me to hook up my meter and deal with my various clips. I can't even get my meter off my toolbox here. Deal with my various clips and all that type of stuff. So we get our generic scanner, get a little interface hooked up here, right? He's talking to our phone, acting as a generic scanner. Yeah, we know we're looking at computer interpreted information, but how does this thing work? Well, this is a thermistor, meaning that it's a resistor that changes its resistance with temperature. And most of these guys are what they call NTCs, NTC, negative temperature coefficient, which means that as they get hotter, their resistance goes down. So if you were to graph it out, and this was hot over here, what you would see is the resistance would drop. The ohms of that sensor will drop as it gets hotter. So where your voltmeter might show 4 volts with the cold engine, it's probably going to show somewhere around 0.4 volts with the really hot engine. Okay, so I'll write hot right here. And cold. Okay, so with that circuit knowledge there, so I don't want to mess with my voltmeter though. I told you that earlier. So if I have my scanner hooked up and I unplug my sensor. So now I think what I'm going to do is I'm going to draw just a red X. I've unplugged the sensor. Okay, so the connector is now not connected to anything. Okay. Well, basically, that's made its resistance go really high. In fact, should be out of limits, infinite resistance, because it's not hooked up to a sensor. Remember we said cold is high resistance. So guess what? I've created really high resistance by disconnecting the sensor. So my scanner right now with the sensor disconnected should read like negative 40 degrees below zero. Boom, freezing cold when I disconnect the sensor because it went really, really high resistance. Okay, well, that's good. Now, what about low resistance? Well, I could take a little jumper wire here. Got my little red jumper wire right there, and I'm going to hook it up to that sensor connector. So now I'm going to draw my little red wire, and now I'm hooking my little red wire up. And so now I've gone to really low resistance. So when I hook up my little red jumper wire, now it's going to think, man, I'm smoking hot. Maybe I'm at 260 degrees or 300 degrees, something like that. So with a little bit of circuit knowledge, I could bypass messing around with my multimeter. Why? Because if I unplug the sensor, I should see my scanner say, boom, the temperature went way down. It's freezing cold outside, right? It went really, really cold. And then when I jumper the sensor connector, now it should say I'm smoking hot. And if it does that, what you've basically done at this point is obviously your scanner and stuff's working, but you've tested the computer and the wiring to the sensor and the sensor ground. You've checked all that out and you know that it's okay. It's good. So if I have a coolant temperature sensor that's not functioning right, and I've done this check, well, I'm gonna have, only a couple things left. It's either I have a defective sensor, or maybe I actually have something wrong with the engine. Like let's say it has a coolant leak and there's no coolant in this, to touch the sensor, right? So if you had no coolant in the engine, then the sensor's not submersed in coolant, it's not going to work correctly, right? So you always have to check for that. But if you do this test, it tells you the computer's doing its job, the wiring's intact, and more than likely what you need to do is replace that coolant temperature sensor. All right. So I just wanted to show you how you apply some circuit knowledge and using your scanner, and this is all with the generic scanner, to shortcut some diagnostics. Okay, so I can't stress this enough, and this is why, we have a whole semester-long class in engine performance that's all about the computer engine controls, all those engine performance things from measuring fuel pressure to how each and every sensor works on the engine. And right now that's like one big 6-unit class at our school. A lot of schools are splitting that up, and we're even thinking about doing that. But you just can't substitute, learning the circuits, because that's how you can shortcut and do your pinpoint diagnostics faster. Okay. All right. So we're going to jump into a little bit of O2 sensor knowledge, or O2 sensor diagnostics, which again, that's going to start with some circuit knowledge, and it's going to require that we learn a little bit about fuel control strategies. So with that, let's jump in. For some of you guys, this might be a good review. For others of you, it might be all new, and it's fine on both cases. So one of the big things that happened as we moved through the 80s, and we were trying to get vehicles to run cleaner and get better fuel efficiency, is we set up a strategy or programming in the computers, and they even had computer controlled carburetors that would do this. But we set up what we called open loop and closed loop. Now, open loop, what that means is that we have a computer in the vehicle, and that computer is trying to get things to run as clean and as efficient as possible. It's going to control the fuel delivery based on what was programmed in the computer. Okay. And so it's going to look at all its sensors like engine RPM, throttle position, maybe manifold absolute pressure or mass airflow. It's going to look at all the sensors except the O2 sensor. Okay. So it's ignoring the O2 sensor in this case. It's using its programming and it's looking at all the other sensors, and it's basically doing its best guess of this is how much fuel the engine should have. Okay. That means it's an open loop. So if it's not in closed loop, it's an open loop. Typically, that means that the air fuel mixtures are richer than stoichiometric, or for gasoline engines, 14.7 to 1. What is this? Well, it's 14.7 pounds of air for every 1 pound of fuel that goes into the engine. Okay. And we do it in pounds because it makes the numbers more palatable. If you did it by gallons, and sometimes I get on a wild tangent and we calculate it out, it would be something like 9,000 gallons of air flowing through the engine to burn 1 gallon of gasoline. It's pretty crazy numbers. So 14.7 to 1, what we call it, we have a fancy name for this. We call it stoichiometric. That means it's in balance, and it's a good air fuel ratio. It's a good proportion between the amount of air that's going in the engine and the amount of fuel that's going in the engine, where it's going to burn that air fuel mixture completely. It's going to run clean and get you decent performance and decent fuel economy. It's kind of like your ideal compromise. So when you think about, hey, what's the goal of the fuel injection system? On a gasoline engine, it's to run at 14.7 to 1 pretty much all the time. Like that's the number one goal, because if I'm running that air fuel ratio, I should be running well, and I should be running clean, and I should be getting good fuel economy. All right. So when we're in open loop, we're not looking at the O2 sensors. We're looking at all the other sensors on the engine and doing our best guess. So what's different when we go to closed loop? When we go to closed loop, now we're looking at the O2 sensor. So what do we need to go into closed loop? Well, we need these things right here. We need the engine to get up to operating temperature. We need adequate time to have elapsed for everything to stabilize. So there's a little timer. Think of a little stopwatch in the computer after you start the car, where it's looking to see enough time has elapsed. Now, on some of the older cars in the 80s, that timer could be 2.5 minutes before it counted down and would go into closed loop. New cars can go into closed loop within seconds, okay, if the engine is up to operating temperature. The other thing you need is you need the O2 sensors actually producing a decent signal. So if your O2 sensor is dead, or it's not producing a good signal, or maybe it's disconnected, well, then I'm not going to go into closed loop. So engine at operating temperature, an adequate time has elapsed, and decent signal from my O2 sensor. Those are the three things that I need. But my kicker here is that I'm operating at a light load condition. Why? Because when you go to wide open throttle, guess what? Your throttle position sensor, your TPS, is going to see that, and it's going to say, hey, this guy's at wide open throttle. Well, wide open throttle, I don't care about running clean. I don't care. I care about two things: go fast and try not to blow up the engine, right? And so when I'm in that mode, when I'm at wide open throttle, I'm typically going to give the engine more fuel and run it richer because that's going to be safer for the engine. It's less likely to blow up and there's extra fuel there to cool the combustion. And it should make a little bit more power. And so that's what they'll do. So if for whatever reason, let's say your throttle position sensor failed and it shorted and it was always telling the computer, oh, hey, he's at wide open throttle. He's at wide open throttle. He's really gassing that thing. Your car would never go into closed loop and it'd be running rich all the time. It'd fail smog. It'd be a gross polluter. And I actually had that happen on several, 1980s and 90s cars. Even on GM had throttle position sensors in their computer controlled carburetors, and those would fail. And it would fail smog because it'd be dumping too much fuel in there. So to go into closed loop, I'm looking at my O2 sensors, and that means I've needed to meet all these conditions. Okay. Those are my enable criteria, if you will. Okay. So moving right along, guys, moving right along. When we go into closed loop operation, the whole goal is that now we can use those O2 sensors and really get ourselves at that ideal air fuel ratio of 14.7 to 1. That's the goal, because we're going to be running clean, or we're going to be running green, if you will, and that will be running with good fuel economy, good emissions, and actually pretty darn decent power as well. So this gets us on the tangent of, well, how's that O2 sensor work? If he's important for this closed loop thing, what's going on with him? Or we're not going to get into all the theory of the different O2 sensors. There's zirconia sensors, there's titanium. We're not going to go into all of that, but we are going to get through some of the basics. Okay, guys? And so what this will do is it will make it a little bit easier to understand when you get to engine performance, or if you've already had it, it's a good review. Most O2 sensors are zirconium. So that's what I'm using for my example here, is zirconium sensors. Basically, they act like a little tiny battery. And somewhere on my workbench, I had a little AA battery, and it's rolled off my workbench, but they basically act like a little battery. And just like a little battery, little batteries can die out. Well, so can O2 sensors. O2 sensors do have a lifespan. The old ones lasted maybe about 30,000 miles. Newer sensors, maybe you get 60 to 90,000 miles, but they do have a lifespan to them. So again, you think of them like a battery. All batteries will eventually go dead. So will an oxygen sensor. Basically, how this thing works, if I look at this graphic right here, he's like an oxygen comparator. He's comparing how much oxygen is on the inside of the sensor element versus how much oxygen's on the outside of the sensor element. Now, what you can't see, because it's not in my picture, is this sensor is screwed into the exhaust pipe here. So what's going down the pipe is exhaust gases on the top body of the sensor. It may not look like it, but here's the top body of the sensor. Here's some wires coming out of the sensor. Oops, I was going to change the color on that. So here's the wires coming out of the sensor. What you don't realize is this top part here is vented, and it's getting air from outside going in the top of the sensor. And he's comparing how much oxygen is outside the exhaust system versus how much oxygen is inside the exhaust system. When you're running rich, there's not a lot of oxygen in the exhaust. So the O2 sensor is going to make more voltage. So if I clear out those drawings, what you'll see here is it says 0.6 volts or higher. The voltage goes up when it goes rich. So I'm going to put a R on this side. And the voltage goes down when it goes lean. I like to think lean is less voltage. So that's kind of a shortened, condensed version of how an O2 sensor works. So it measures the difference between the air outside and inside the exhaust. The difference of those two chemically causes a voltage to be produced. And again, think lean is low or lean is less. So if I'm lean, I'm down here. If I'm running, I guess I could have done that as blue or something. If I'm lean, I'm down here. And if I'm running rich, then I'd be up here. So notice this. If the O2 sensor says, hey man, you're lean, the computer says, okay, go rich. If the O2 sensor, right, this is the O2 sensor, if he's reading 900 millivolts, that's the signal he's producing, it tells the computer, hey man, you're running rich. Okay, what's the command? Go lean. The command is always the opposite of the condition. I'm going to type that out. The command's opposite the condition. So when the O2 sensor goes rich, the computer then says, okay, now go lean. When the O2 sensor says, hey, I'm lean, now the computer says, okay, go rich. And what you end up with is your air fuel mixture and your O2 sensor signal going rich, lean, rich, lean, rich, lean, rich, lean. And when you average out these riches and these leans, what you end up in the middle with is that stoichiometric or ideal air fuel ratio of 14.721. Okay, so that's in a nutshell what's going on with closed loop and the oxygen sensors, all that type of stuff. A typical zirconia sensor, its maximum voltage you get off that thing is 1.2 volts. So it's a tiny voltage signal. Okay, so less than 300 millivolts, it's going to be low voltage. That's lean. More than 600 is going to be read as rich. And again, the computer's command is always going to be opposite the condition. A normal O2 sensor, we've been talking about, hey, you got it a normal, is going to be switching back and forth somewhere between 100 and 900 millivolts. Okay, so a little less than a volt. And it should have 3 to 5 transitions every couple of seconds in the car. Okay, now if you had an oscilloscope on it and you're really doing a response test, it should be able to go from lean to rich, or from 0.1 volts to 0.9 volts. And actually, we usually scoot that down. We go between 0.2 and 0.8, but it should be able to do those within 100 milliseconds. And I've tested hundreds of O2 sensors with my oscilloscopes over the years. And what you'll find is like a brand new sensor usually will do it in less than 40 milliseconds. So a lot of them be like 37 milliseconds, 35 milliseconds, 39 milliseconds. Brand new sensors usually can do it less than 100 milliseconds. When a sensor starts getting kind of tired, it's 80 milliseconds, 90 milliseconds. A sensor that's really getting lazy and slow will take over 100 milliseconds, and a good OBD2 system will actually set a code for that, for O2 sensor performance. All right. Contaminated sensor, bias sensor. So here's some shot of contaminated sensor. All types of things can contaminate these sensors. If you got a hold of some leaded fuel, if you put a bunch of silicones to seal up your intake manifold, those could ruin your O2 sensor. excessively rich mixtures. There's the silicone one, too much RTV. Here's probably the most common one that I still see is you have a car that has mechanical problems. It overheats, it blows a head gasket, and it's burning coolant in the engine. Well, guess what? Not only you have to deal with the head gasket and that mechanical job of replacing the head gasket, maybe having the head milled and all that type of engine work, but burning the coolant likely wiped out all your oxygen sensors. So if that's a V8 engine with multiple sensors, you could be replacing 4 additional sensors. And guess what? You know who else doesn't like that coolant pumping through there? The catalytic converter. So that blown head gasket, if you keep driving on it and driving on it and driving on it and, you know, filling up the coolant, driving a little bit more and filling up the coolant, driving it some more, you'll end up costing yourself more money in the long run, because when you get the car fixed, now before it's passing smog, you're probably going to need multiple oxygen sensors and even a catalytic converter, because the coolant will contaminate all those things. Leaded fuel, I mentioned that. All right. So a few weeks ago, we talked about, hey, give me your case studies. Give me some information of what you're working on, what you're afflicted with. And so I had a student in the class, had a 98 Lexus. So it's an early OBD2 vehicle, ES300. And he was fighting this particular code right here, a P0420. And of course, why is he fighting it? Well, now he's up for smog, and the check engine light's on. So it's going to be a failed smog check, right? So again, we would use our troubleshooting process, and it's good to apply some circuit knowledge. So we would verify the complaint. Yeah, it's got a check engine light on. Pull the codes, record them. We got that P0420. Look at the scan data. Or the freeze frame data. Oh, it happened when they were going 65 miles an hour down the freeway. Okay. So we can simulate that again. Now we got to have some knowledge as we start looking at scan data. And so we talked about this cycle limit theory of normal operation of the O2 sensor. So this is what it should look like. The other ones are not what you want, right? Well, I should say this is what it should look like for a sensor 1. That means that sensor is before the catalytic converter. Okay, so the sensor before the catalytic converter, that's the one that controls open loop, closed loop, and really is the primary driver of your fuel trim. Well, what about, I have a car, it's OBD2, I got multiple oxygen sensors. Maybe I got 4 oxygen sensors. Well, the 2 ahead of the catalytic converter, well, those guys are there to control. Those guys are there to control the air-fuel ratio and help the engine run correctly. The sub-oxygen sensor, the sensor 2, he's there to monitor the cat. He's there to know, hey, what's that catalytic converter doing? Now, they might do a little bit of trim and stuff on them, but primarily the O2 sensors behind the catalytic converter, they are there to check the operation of the catalytic converter. So this is what it should look like. If I had a good catalytic converter, this is my normal condition. My O2 sensor, bank 1, sensor 1, before the cat, switching back and forth. Rich lean, rich lean, rich lean, rich lean. It's in closed loop. My O2 sensor after the cat, it might have some trending, and then when I'm cruising on the freeway, he's just pretty flatlined. Why is that? Well, inside this catalytic converter, you guys know that there's precious metal in here. This is why the catalyst thieves steal our catalytic converters. Drives us nuts, right? There's precious metals in here. There's platinum, palladium, rhodium, cerium. That cerium part of the substrate, it actually stores oxygen and then uses that oxygen to help burn the emissions. So you guys might not realize it, but the cat, he's going to try to burn any emissions the engine doesn't burn up. So if your engine's running really poorly, that's just going to make the cat work over that much harder. Okay, the cat's going to try to burn any emissions the engine doesn't burn up on its own. So the better your engine is running, the less work the cat should have to do. In fact, a cat that's running, or an engine that's running really, really good, that's well designed, you know, I've found time after time that it can meet the California state emission standards without that catalytic converter on there most of the time. When it's nice and hot and, you know, running really good. But the cat helps it out when, you know, to get it not just to passing, but below passing, and to make sure under all operating modes that it is, you know, having low emissions. Anyways, so because the cat stores oxygen and then it releases the oxygen and burns the emissions, that's why the O2 sensor after the cat is going to be pretty flat, pretty smooth. Now, if I get on and off the throttle, it's going to go rich. And if I get off the throttle, it's going to go lean a little bit. But by and large, it's going to be pretty smooth. So we say it's throttle sensitive, but it shouldn't be changing rapidly with mixture. Okay. So this is what it should look like. When the catalytic converter is degraded, when the precious metals are all consumed out on the inside, well, then what happens is the O2 sensor before the cat and the O2 sensor after the cat, they look the same. And that's how the computer knows that, hey, these things are pretty much the same. They're both cycling at the same frequency. I must have a defective catalyst. That's how the catalyst monitor works, is it waits for you to be driving at a good steady speed, a good amount of load, but not too much load, easy on the throttle, steady throttle, and it's comparing before and after. They should, the one behind the cat should be nice and smooth. And if it's not, it's going to set that code. So if I go back to this car, right, if it's setting a P0420 for degraded catalyst low efficiency, that is what I'd be looking at. I'd set up a custom data list, and I look at my O2 sensors both before the cat and after the cat. Now, I don't know about you, but when I'm trying to drive a car and do a test drive, and it seems like everybody out on the road, their goal is to get in my way and slow down and cut me off and, you know, try to, you know, get me into some type of a wreck. So being able to record the data is really nice, because then I don't have to look at my scanner screen as I'm driving around. So on our older Snap-on tools, a lot of them call them, Snap-on called it movies. Most other manufacturers' tool called it a snapshot. But basically, the recording allows us to record that data and look at it later. So in the case of the catalyst, I would put on my data recording feature. I would turn this on and I go test drive it. And then I would pull off the freeway, stop my, you know, I'd stop my recording, I'd pull off the freeway, and then I would look at that data. So I didn't have to worry about, you know, stop and go traffic catching me out when I was looking at my scanner screen. So our tool, our generic little free app with our $20 scantool interface, it actually has the ability, this is one of the things I really like about it, to do some data recording. What you do is you basically, oh, where's the menu at here? We get to a scanner screen here. And I'm going to change my screen. Share screen, go to this one. Let's see if I can find the screen I want. There we go. That'll work. So if you look right here, you got this little thing that says record. You click that thing. You click that icon. When you click that icon, the next thing you get is this splash screen coming up. And it says, hey, do you want to enable recording? Click OK. And what it will basically do is always record your data when you do it right. So this is one of those cases where I always say, hey, read what it says on the screen. So let me make this screen a little bigger. Let me make this screen a little bit bigger here. And there it is. Okay. So it says you can enable the recording of data for viewing for later. To review that recorded data, it only saves it when you tap on the disconnect button. So what that means, you could be recording data, and if you just like turn your cell phone off, or if you just unplug the scanner, if you don't shut it down correctly, it will not save that recording. It's always recording it in a data buffer, but it won't actually save it unless you actually go in here and hit disconnect. And then once you do that, you'll see a file saved with a time and date stamp of when your recording is for you to review. Okay, so when you get a dialog box like this that comes up, always read it, right? Always read what that says. So I recommend to always do data recording so that you can focus on driving and you don't get in a wreck with your customer's car as you're trying to diagnose it. All right, so leverage as much as you can for your scan tool. So tonight, when we think about leveraging it, our scan tool, we talked about building custom data lists. We talked about graphing that data and tailoring what data you're looking at to the code that you're fighting, the big 6 and the great 8 data parameter pits, right? You can also use your O2 sensor and fuel trim to establish a condition, meaning that, hey, if I'm running rich, I can look at my O2 sensors. If they constantly are saying rich, okay, well, something's causing this engine to run rich. If I have a lack of power complaint and I go accelerate the car, I'm getting on the freeway, and I notice that the whole time I'm accelerating, the O2 sensors, both banks, they're saying lean, 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 lean. If I'm lean all the time, then I've established that condition. I have a lean running deal. So maybe I have something as simple as a restricted fuel filter or a fuel pump that is starting to fail. So you could use the O2 sensor information along with fuel trim, and we'll get more into fuel trim in our next class session to kind of expand on that a little bit more. To really establish a condition. Am I running rich or am I running lean? We also applied some circuit knowledge. And so this is where I got to be honest, there's no substitute for knowing the sensors, right? You really want to know how those sensors operate. Here's what's great is an O2 sensor on a Chevy will work really similar to an O2 sensor on a Mazda, and like zirconia O2 sensors or zirconia O2 sensors. Throttle position sensors are mostly all the same. There's 2 groupings, the potentiometer style and the Hall effect style. But once you start learning these sensors, it doesn't matter what car you're working on. A lot of the sensors will work the same basic way. Okay, so over time, this will get easier and easier because you'll see the commonalities. And I'm always looking at cars and I go, oh, that's just like a Chevy, or that's just like you know, a Toyota or whatever. You'll start to see similarities. A lot of cars, honestly, they'll use the same components. They'll reach out to the same supplier, whether that's, you know, Nip and Denso or whoever, and they'll use the same components to make them work. So always use freeze frame data to meet your enable criteria to verify your repairs, right? So those are some of the things that I was hoping that you would take away from tonight. I showed you different ways to look at your scan data, and we ran through some different diagnostic scenarios. So hopefully that hopefully at this point your brain is full. Hopefully it's not too full, but you're feeling good and you got some stuff out of it. Remember my tip about do not clear the codes until you're done with your repairs, right? So that's the information I had for you tonight. If we exit out of this presentation here and I go back to our Canvas page, you can see what assignments and stuff are coming up. I always like to look through the modules, but I know a lot of students, they like to skip right over here and go to assignments and look at stuff this way, and that's fine too. You know, and you can go to assignments and then you can just look at these little date codes on here. That one was due September 10th, so you can see where we're at. So we've done the protocol one, and now we're moving on to what diagnostics do you need? And of course, we're past the 11th. So let's clear some of that stuff out. So now we're moving into the one that's due here in just a few days. Is this one, codes, custom data list, and data recording. This perfectly lines up with our presentation for tonight. There's also going to be a little discussion there on the different modes of OBD2. That one really lines up with our previous class when we looked at all different 10 modes of OBD2. And then coming up after that, we're getting into some diagnostics and some fuel trim information. So let's look at this one that's due right away. So what you're going to do with this one is you're going to look for codes and pending codes. You're going to look at the data. If you click the all sensors, if you click this this guy right here, all sensors, it lets you look at all the parameters, but it's not a custom data list. If I want to do a custom data list on this particular little tool, what I got to do is click live data. Then I can select between 2 to 4 different PIDs, depending upon what version of the app I have, to set up a nice little custom data list and graph that data out. And so this activity is basically going to ask you to do just that. It's going to ask you to graph out a couple of PIDs. It's going to ask you to look at all the data and look at how many PIDs are listed. Look at stuff at 2,500 RPM and at idle. And basically, you're going to take some screenshots and do some data recording and do a lot of the things we talked about tonight on your little scan tool. Now, if you don't have this particular scan tool, that's okay. You can use any scan tool you want for this class. You could use the Snap-on Solus. You could use an Altel, whatever tool you want to use. Here's what I want you to do. If I want you to go through there, I want you to pull codes. I want to see if you have any codes. Then if you have codes, I want you to look at the freeze frame. Okay. Now I want you to look at all your data and figure out how many different data PIDs, how many different parameters there are. That's like engine RPM, throttle position, mass airflow, coolant temp. There might be a canister purge, desired idle. I mean, how many things are listed there? Transmission shift solenoids. There could be 100 different things there. Then I want you to make a custom data list. If you have a scanner that could graph like 8 different things, or do the big 6 or the grade 8, do as many things as you can. Try to graph stuff out versus just looking at stuff in a numerical format, and take screenshots of this stuff. Or if you're using a traditional scanner, you can always take your cell phone to take a photo of what's on the screen of that scanner. Okay. And lastly is see if you can make a data recording. You just got to go for a short test drive, right? Nothing like an hour, just 1 or 2 blocks, take a quick recording and review that information there, and send me some screenshots of that. Okay, so it's just, this assignment is to try to force you to run your scan tool through its paces. And again, you can be using our little Car Scanner Pro app with your cell phone interface, or any scanner that you have. It just has to do the 9 or 10 different basic modes of OBD2. Okay, so with that, that's probably a good place to kind of wrap things up. Question in the chat: is there a way to adapt our Car Scanner Pro to OBD1? No, there's not. You would really need a more powerful scan tool to do OBD1. That you remember, OBD1, every car had a different connector, cars had different protocols. So you're going to need more of a professional level scan tool to get in those older vehicles, those OBD1 vehicles. Here's the great thing about that: if you have an older vehicle that's OBD1, you can buy used professional level scan tools really cheap these days, because people aren't working on old cars anymore. So you can get a scan tool that used to cost $5,000. You might be able to get it for $100 or $200, because it only works on the older vehicles. So what I would say is, hey, if you're going to work on older cars, if that's something that you want to do, then I would be, searching Craigslist and the different message forums and garage sales and stuff, and state sales, and try to get your hands on a professional tool that's used to do OBD1 vehicles. I still have my old Snap-on red brick, and I still use it because obviously I have a lot of old vehicles, but that's what I would recommend you do. Remember, older vehicles are mostly going to give you trouble codes and then scan data. That's it. There's no freeze frame. There's nothing else. It's trouble codes, scan data. And if it was a car with really good diagnostics, like a GM vehicle, you might have some bidirectional controls where you can change the idle speed or activate the EGR valve or something like that. Okay, so definitely, if you want to scan some OBD1 stuff, I would encourage it. It's not a requirement for this class. And it's one of those things where it would be kind of a bonus activity. If it's something you're really interested in doing, though, you can come to my skill and speed class on Friday from basically 9 to 2. Show up on Friday, bring your OBD1 car, and we'll figure out a way to scan it. Okay. So good questions. Thank you for participating tonight. Again, I will give you guys some credit for being here and doing that stuff. I really appreciate it. So with that, I'm going to wrap things up. Thank you so much for being here tonight, and I hope to see you in our next class, which won't be next week, but it'll be the week after that. We're going to dive deeper into fuel trim and start doing more case studies and diagnostics. Okay. All right, everybody. See you next time.